Pluto made them come from the beginning. It was like it never had a spot. Pluto's circle crosses that of another planet that is no kind of direct for a planet. Pluto, once considered the 10th planet of our planetary gathering, was renamed as a Peewee planet, generally due to its uncommon orbit, which deviates significantly from the ordinary orbits of the large planets. Despite its diminished status, Pluto remains a subject of interest and study in the cosmic neighborhood. Later assumptions by leading analysts have included the potential risk introduced by Pluto's orbit, which brings it unsafely close to Neptune's orbit. This alert was sounded by astrophysicists Neil deGrasse Tyson and Michio Kaku, who propose a possible scenario wherein Pluto and Neptune could influence each other, presenting a critical risk to Earth and other heavenly bodies in our solar system. Pluto's orbit around the Sun is characterized by its unique properties. Unlike the relatively round orbits of the large planets, Pluto's path is significantly elliptical, meaning it changes substantially in distance from the Sun throughout its orbit. Additionally, Pluto's orbit is inclined at an angle of 17 degrees to the ecliptic plane, further distinguishing it from the orbits of various planets. Despite the crossing paths of Pluto and Neptune, a collision has not occurred up to this point. This is attributed to the gravitational effects applied by various planets in the planetary gathering, which have helped stabilize Pluto's orbit and forestall catastrophic accidents. The examination of Pluto's orbit has revealed unique and fascinating characteristics, including azimuthal libration, scope libration, and the VK faltering. Azimuthal libration refers to the spatial relationship between Pluto and Neptune when Pluto crosses Neptune's orbit, ensuring a minimum distance between the two bodies. Scope libration incorporates the vertical movement of Pluto in relation to the orbital plane of Neptune, providing an additional layer of confirmation against collisions. The VK influence, named after the researchers von Zuyl and Kai, describes the gravitational interactions between Pluto, Neptune, and the Sun, influencing their independent orbits. While Pluto's orbit shows robustness over short timescales, numerical simulations have revealed its turbulent nature over extensive time periods. Minor deviations in starting conditions can lead to significant differences in Pluto's orbit, highlighting the challenges of predicting long-term grand components. Taking everything into account, the examination of Pluto's orbit offers critical insights into the complexities of space mechanics and the interactions between celestial bodies in our planetary gathering. By understanding these components, astronomers can better grasp the past, present, and future of Pluto as well as other distant worlds and stars. The unique properties of Pluto's orbit have been found to maintain integrity over incredibly long timescales, effectively keeping chaos at bay. Continuous virtual simulations have shed light on how the gravitational effects of the gas giants like Neptune, Jupiter, and Saturn play a critical role in shaping Pluto's path around the Sun. Particularly, Neptune's gravitational influence creates a notable resonance with Pluto, ensuring a stable orbit. Jupiter's gravity also significantly contributes to maintaining Pluto's orbit, with Saturn providing additional support. The interplay of these gas giants works in concert to safeguard Pluto's trajectory through space. Sorting out these characteristics is crucial for maintaining the stability and consistency of celestial dynamics within the universe. Without the gravitational influences exerted by the gas giants, the nearby planetary group would be far more chaotic, and bodies like Pluto could collide with other celestial objects or be ejected from their stable orbits, triggering a ripple effect across the entire planetary gathering. The example of Pluto highlights the importance of understanding the dynamic nature of the planetary group. Despite initial uncertainties and debates about its status, continuous observation and study have revealed how Pluto achieves harmony through the intricate interaction of gravitational forces and orbital mechanics. This underscores the need for ongoing research to broaden our understanding of our place in the universe. Pluto's orbit serves as an ideal illustration of the unconventional nature of celestial bodies, demonstrating the potential for orbital chaos where even slight variations in initial conditions can lead to vastly different long-term outcomes. Numerical simulations have been instrumental in deciphering Pluto's developments, showing how minor changes can significantly alter its path over great spans of time. Regardless of the apparent strife, Pluto's orbit maintains a remarkable stability over billions of years, demonstrating resilience amidst apparent chaos. Predicting infinite events, particularly those involving eccentric orbits like Pluto's, presents significant challenges due to the inherent unpredictability of these systems. Numerical simulations offer valuable insights into the future paths of celestial bodies but also highlight the limitations of our current capabilities, as they rely on precise initial conditions and complex interactions. Additionally, Pluto's volatile orbit underscores the ever-evolving and dynamic nature of the universe, reminding us of the limitations of our present understanding. While significant advancements have been made in unraveling the mysteries of space, the existence of Pluto serves as a humbling reminder of how much we still have to discover. Neil deGrasse Tyson's perspective on Pluto's journey exemplifies the ongoing evolution of how we interpret the planetary group. His contributions, both in scientific research and public engagement, offer critical insights into the complexities of celestial mechanics and humanity's enduring curiosity about the universe. Tyson's view on Pluto's renaming reflects a broader appreciation of our solar system's complexity and evolution. He sees the renaming not as a downgrade but as a significant change in our developing knowledge of the celestial bodies surrounding our Sun. Tyson advocates for a continuous course of learning and adaptation in our understanding of celestial mechanics, suggesting that anomalies like Pluto's orbit serve as markers of the vast unknowns of space. He believes that the pursuit of these questions makes cosmology so fascinating. Furthermore, Tyson emphasizes the importance of celestial events and discoveries in nurturing public interest in cosmology. He views occurrences like Pluto's renaming and its orbit's peculiarities as opportunities to spark society's imagination and curiosity about the universe by examining the dynamic and sometimes bizarre nature of space mechanics. Tyson means to develop a more significant appreciation for the supernatural occurrences and privileged insights of the universe among the general populace. Notwithstanding his work as a science communicator, Tyson, alongside various analysts, has raised concerns over the possible risk introduced by Pluto's irregular orbit. After significant stretches of study, Tyson warns that the three-body issue, including Pluto and its possible collision with Neptune, is a genuine concern. He highlights that such a collision could upset the delicate balance of the universe and have disastrous results, potentially affecting Earth and other celestial bodies. Michio Kaku, renowned for his work in speculative physics and string theory, offers a unique perspective on the conversation surrounding Pluto's orbit. He sees the examination of Pluto and its orbit as instrumental in shaping the inevitable destiny of space exploration. Kaku believes that understanding the gravitational associations and orbital components of celestial bodies like Pluto can provide significant insights for future space missions, assisting with course risk assessment and planning missions to the outer reaches of the solar system, as well as beyond. Kaku frequently discusses the important relationship between celestial mechanics and theoretical physics, highlighting that peculiarities like the gravitational dance between Pluto and Neptune are not isolated events but are significantly related to the fundamental principles of physics. His work in string theory aims to explain these principles, suggesting that a focus on celestial mechanics can offer insights into the secret laws of the universe. Both Tyson and Kaku provide significant perspectives on the discussion surrounding Pluto's orbit and its implications for our understanding of the universe. Their insights highlight the interdisciplinary nature of space science and emphasize the importance of continual research and focus in unraveling the mysteries of space. The potential collision between Pluto and Neptune presents more than just a monumental celestial event, it offers a unique opportunity to test the assumptions of string theory, particularly those associated with gravity in spacetime. The gravitational waves generated by such a collision could convey marks or anomalies that may align with or challenge the assumptions of string theory. While the immediate impact on Earth would be negligible due to our distance from the outer solar system, the broader implications of such an event could be significant. They could substantially influence how we interpret the fundamental concepts of the universe as depicted by string theory and other areas of theoretical physics. Pluto's orbit serves as a vital illustration of celestial mechanics in action, displaying both stability and chaos within our planetary system. Its unique characteristics, influenced by the gravitational forces of neighboring planets, particularly Neptune, highlight the intricate and dynamic nature of space. the potential collision between Pluto and Neptune is merely one example of the various mysteries that still require our exploration in the universe. Other potential disasters, such as planetary influences in space, are expected to occur. Orbits vary over time due to a range of factors, including gravitational interactions described by the three-body problem. Structures like the TRAPPIST-1 system, where multiple planets orbit closely together, illustrate how gravitational collaborations can create orbital resonances, potentially provoking destabilization over time. While such influences are not occurring in these systems at present, scientists actively monitor them to gain insights into how planets affect each other's trajectories. Planets drifting through space without a star add another layer of complexity. These planets can be ejected from their original star systems due to gravitational disturbances or other significant events and can travel vast distances, potentially colliding with other star systems. However, the sheer size of interstellar distances and the relatively small size of rogue planets make such crashes improbable. Vast interactions can also disrupt the orbits of stars and planets within merging galaxies, leading to violent ejections or collisions. While direct planetary collisions are unlikely during these events, the gravitational disturbances can still impact celestial bodies within the affected galaxies. Recent studies suggest that gravitational disturbances from outer planets led to a period of increased comet and asteroid impacts on Earth roughly 40 million years ago. This anomaly, although excluding planetary collisions, shows how gravitational interactions can shape celestial bodies' trajectories and influence the geological history of planets like Earth. Overall, the study of celestial mechanics and the potential consequences of massive events like planetary collisions offers significant insights into the dynamic and ever-changing nature of the universe. Through continued research and investigation, scientists can enhance our understanding of these phenomena and their implications for our place in the cosmos. As stars evolve and lose mass over time, the orbits of planets within their systems can undergo dramatic changes, potentially leading to merging orbits. This phenomenon is particularly evident in systems where stars reach the end of their life cycles. As a star ages and exhausts its nuclear fuel, it undergoes significant changes in mass, especially during phases like the red giant stage or when it sheds material in a planetary nebula. These changes in stellar mass substantially affect the gravitational equilibrium of the system, causing the orbits of surrounding planets to either expand outward or become more compact. This phenomenon is more pronounced in multi-star systems, where complex gravitational interactions among multiple stars can lead to unstable orbits more rapidly. In such systems, the gravitational pull from different stars can interact in unusual ways, disrupting orbital patterns and increasing the likelihood of orbital crossings. Consequently, situations may arise where planets are captured by another star in the system, collide with other celestial bodies, or even get ejected into interstellar space. Despite these possibilities, the actual occurrence of planetary collisions is still considered highly unlikely. The vast expanse of space and the relatively small size of celestial bodies make direct collisions rare events. Nevertheless, these potential outcomes remain of great interest to astronomers and astrophysicists, as they offer valuable insights into the dynamics of planetary systems and the evolution of galaxies. The exploration of Pluto's orbit represents the ongoing quest for knowledge and understanding in the field of space exploration. As articulated by Tyson and Kaku, each discovery and new piece of information brings us closer to unraveling the complexities of our universe. This journey challenges our perceptions, expands our horizons, and serves as inspiration for future generations of explorers and scientists.